There are no industries in space at the present, but there soon will be.
What does dust from space tell us about ourselves? What happens next if we find life on Mars? And should we mine rocks in space? All of this and more in this episode of the Earth-Size Show. Now, I'm glad that I'm joined with Dr. Matt Genge from Imperial College London, who is a planetary scientist and geologist. And he's actually an expert on cosmic dust, which we'll be talking about quite a lot in this episode. So stay tuned. As always, my name's Orion Shah, and you're listening to the Earth-Size Show. So, Dr. Genge, what is cosmic dust and what makes them so special?
Well, you might not be surprised to learn that cosmic dust is just dust from outer space. And it's that dust that lands on Earth that we then recover as what we call them micrometeorites. And essentially, they're just tiny little meteorites. So they provide us with a sample of small objects within our solar system, things like asteroids and comets. And what they tell us about ourselves is they formed during the formation of our solar system. So asteroids and comets date all the way back before there were planets, when our solar system consisted of a young star, the young sun, surrounded by a disk of dust and gas. And it was in that environment, in that disk, that dust grains started sticking together to make larger dust grains, which stuck together to eventually make asteroids and then planets. And cosmic dust records that formation, the events that occurred during the formation of our solar system.
Wow. I don't think people realize just the importance of things like that, because on the news you see, okay, there was a meteorite across the sky, there's asteroids in space, but nobody really understands just how significant they are. And especially considering that, geology was thought to be the study of rocks and the earth. But now geology has been redefined as a study of just rocks in space and on our planet and all these other planets as well. So that's quite fascinating indeed. And for our audience members who don't know, a meteorite is a rock in space that's formed after a few collisions. And when it comes down into our atmosphere, that's a meteorite. You can actually see them if you look in the right place at the right time. So keep a lookout if you really want to. But yeah, that's a meteorite.
You do have to be quite lucky to see a meteorite fall. So meteors you can see all the time, the little shooting stars, and those are things about a centimeter in size that are coming through the atmosphere, and they completely burn up. Meteorites make up what's called a fireball, and you really will notice if you see one of those. They're really bright, they're associated with sonic booms, and sometimes they produce an electromagnetic pulse that causes your ears to crackle. Can you imagine that? Can you imagine having such a strong electromagnetic field that you can hear it in your ears?
Wow, I didn't actually know that. That's quite fascinating indeed. Yeah, I didn't think I knew much about meteorites before, but I think as we go on through this episode, myself and also the audience will learn quite a lot about it. So that's great. And so on the topic of micrometeorites, I read that they're everywhere, on our clothes, on the streets, on the roofs of our houses. Why is that important?
So, yeah, dust falls all the time from space because the Earth is moving through quite a diffuse cloud of dust called the zodiacal cloud. And about 10,000 tons of dust lands on Earth every year. And that works out to about 6 particles per square meter per year.
Wow.
So that really does mean they are literally everywhere. But I don't know how clean your house is. My house, fairly clean, but still, it would be a challenge to find 6 extraterrestrial dust particles amongst the layers of terrestrial dust that we get. And so when we look for micrometeorites, the best places to go where they're most easy to find, because, you know, I am basically lazy, is to go to somewhere like Antarctica, where there's very little terrestrial dust that can be mistaken for micrometeorites, for cosmic dust, or to the very deep oceans far from land, because there, the mud that builds up on the bottom of the ocean can build up at less than 3 millimeters per 1,000 years.
Wow.
And so the micrometeorites become a really significant proportion of that sediment, and they're much easier to find. So although they fall everywhere, you will have on the top, I guarantee, on the roof of your house, there will be some cosmic dust right now.
That's amazing. Just, I don't think anybody realized that this much extraterrestrial elements and substances, that much of it would be present in our own homes. So that is very shocking to hear. And
Yeah,
when I read
absolutely.
that,
Yeah,
I was
yeah.
just, like, what?
But
So,
isn't it cool to think that you might be wandering around with this tiny little dust particle on your shoulder, and that dust particle could come from an asteroid like asteroid Bennu that OSIRIS-REx is just, the mass emission OSIRIS-REx has just visited, or it could have come from a comet, which is now speeding out of our solar system to be lost into interstellar space. And
yeah,
that dust particle formed before the planet Earth existed.
that is truly mind-boggling, I've got to admit. And I'm sure the audience can agree with me on that one. So
Well, it's
considering,
fundamentally,
pardon,
yeah,
go
it's
ahead.
fundamentally cool, isn't it? It's fundamentally cool, isn't it? Really, you know, even me, even though I've studied them for years and years and years, I still occasionally sit down and go, "Oh, these things are actually really cool."
Yeah, especially when you look at the bigger picture. I mean, to some people, it just may be, a few grains of dust, but to some other people, like yourself, like myself, it's actually part of a bigger equation about, the formation of our planets and things like that. So it really
Well,
depends
I'll
on how
tell
you
you what,
look at it.
but still, my kids find it boring. Oh, Dad, shut up about the dust, please.
It's not for everyone, I guess. Yeah. So then, considering that micrometeorites and meteorites in general, they come from the same place, what is there different to learn about micrometeorites?
So they do come from the same place. If you, by place we mean the asteroid belt or the Kuiper belt, where most of the cometary nuclei are, or out in the Oort cloud. But meteorites, being larger lumps of rock, are delivered differently to the Earth than cosmic dust. So for a meteorite to get to Earth, this larger lump, this fist-sized piece of rock, it needs to be separated from an asteroid in a collision, producing large lumps and lots of dust. And then it kind of needs to be bounced around the solar system in a game of gravitational snooker
Okay.
and accidentally run into the Earth, to cross the Earth's path at exactly the right time to be captured by the Earth's gravity. So there's a very low chance that meteorites get delivered to the Earth. Whereas the dust, because it's so small, it has so little mass, it's affected by light from the sun. So
Okay.
really tiny dust particles, things that are about a nanometer in size, and that's a billionth of a meter, really tiny. They are so light they can get pushed away from the sun by light, by
Wow.
photons of light. Because photons, light has no mass. It has no rest mass, which is why it travels at the speed of light. But it does have a momentum. So photons of light have a momentum. And as we know, when something with momentum hits a solid object that also has momentum, it changes its velocity.
Yeah, correct.
And so that's called radiation pressure that blows away from stars. And stars are very good at blowing away small dust particles. But when dust is slightly larger, and this is really cool, by the way, when dust is slightly larger, it's affected by something called Poynting-Robinson light drag.
Okay.
Really cool name. And the effect is it's relativistic. So there is a slight correction to the angle of incidence of the photons. So they're not actually radial from the sun. They're not directly away from the sun. They're slightly ahead of the particle. And so they slow the particle down in its orbit.
Ah,
It's
okay.
kind of like a friction in space due to light. And that means dust particles between, a few microns to maybe a millimeter in size are slowing down in their orbits. That makes dust particles spiral in towards the sun very slowly. And that means that they're much more likely to be captured by the Earth.
Ah, okay, right.
So dust particles should provide us with a much better sample of what's out there. So meteorites provide us with a lot of information about a few bodies. Extraterrestrial dust, cosmic dust, provides us with a small amount of information of a whole lot of objects in the solar system. So they complement each other.
Okay. I mean, I didn't realize the scale of that. I mean, naturally, you'd think that the dust, it's not as, significant as the meteorites themselves. But after hearing that, it's actually the opposite. The dust themselves are more significant in terms of how much we can analyze from them in the lab and what we get to know about the galaxy and the solar system.
Well, one of the great things about meteorites and the materials of asteroids and comets is compared to rocks on Earth, they are very, very fine grained. The crystals that they contain are absolutely tiny. They are nanometers or in size, which means that that even in a particle that's only 100 microns across, so a human hair is about 300 microns across. Even in a particle that's the width of a human hair, it contains millions of tiny mineral grains for us to study. Whereas, on Earth, if you pick up a random rock, most of the mineral grains in that rock will be bigger than cosmic dust. And if you smash them to pieces, all you'd have is all your dust grains would consist of just one mineral. And there wouldn't be much information you could extract from them.
Okay. That makes more sense. Yeah. That that's quite mind-boggling to think about. Again, I've said mind-boggling twice because this stuff really is amazing. Just to think about the scale of it, and the expanse of space and where they come from, and just how significant they are to us, and what it brings to the table. That is just crazy. Okay, so I'm taking a bit of a detour from meteorites here, and this is probably something that the audience are dying to hear about. But what is the next step for space agencies like the ESA and also NASA if we find life on Mars, whether it's microbial or highly intelligent?
So it's almost certainly going to be simple life forms, unless it's visiting Mars and we happen to bump into it. It's very unlikely to be intelligent, and they probably visit us first. And I'm afraid my answer is going to be a little bit disappointing. So probably the first discovery of life on Mars will be followed by confirming that it was the first discovery of life on Mars. So imagine this for a second, that let's say Perseverance, that's on Mars right now,
Yeah.
looks at some rocks and sees a live bacteria on the surface, or an algae, an algal mat. Now, one would think that that's really conclusive evidence of life on Mars. But spacecraft have landed on Mars in the past. How do
Ah,
we know that's not terrestrial contamination? And
right.
that's something we'd need to evaluate really quickly. Or the very first step would be evaluating if it really is an indigenous Martian organism. Now, if it's fossilized, then it's much better, because then we can say, well, that was used to be alive in the past on Mars. It can't be anything to do with our activities. But still, fossils are often open to interpretation, especially fossils of microorganisms. So we know from looking at rocks on Earth, we can find fossils of microorganisms dating back 3.5 billion years.
Correct. Yeah.
And yet, unless you find a really fantastic example, there's still open questions about whether that's really a microorganism or not. And if you talk to some of my colleagues, like Professor Mark Sefton, who's the head of department at Imperial, he will tell you that he's already discovered life on Mars because he was involved with the discovery of methane and the measurement of methane on Mars. And one of the theories behind the presence of these plumes of methane is they are being released by microorganisms.
Okay. That's quite
So it's
interesting.
possible we've already discovered it, but we have yet to confirm it.
Right. And then, so what do you think about the Allen Hills asteroid or meteorite that was discovered in 1984? Because that had microfossils in it, and
Yeah,
everybody
it did.
thought that there was
Yeah.
life on Mars after that.
Absolutely, and it was. I know a lot of people who worked on that, and I think it was the right decision for NASA to hold a press conference and publish that results, because it sparked a good 20 years worth of research. Really, that was the moment that astrobiology became cool. And what we learned in the years after that um, was that you can fossilize bacteria in a meteorite on Earth in 70 days in a drawer in a museum.
Oh,
And so you have
okay.
to be very, very careful with meteorites, because, of course, this was a meteorite that was found in the Antarctic. There's not a lot of microbial activity in the Antarctic, but there is some. And so most likely those were terrestrial bacteria, or
Okay.
they may have been artifacts caused by the preparation of the specimens. And it was a really good example of how careful you have to be, and how much evidence, how much conclusive evidence you need to be able to claim you've discovered life on another planet.
Yeah. I mean, I guess that would have had everybody on the edge of their seats, because on Earth we do get quite a few meteors and such from Mars itself. And
Yeah,
so,
we've got I think it's about 80 now meteorites from Mars that we've
wow.
recovered, and so they fall all the time. But Mars is much less likely to have life than Earth. It's likely to be, if it is there, it's likely to be fairly sparse. And of course, a microorganism that evolved on Mars is very unlikely to be able to infect life on Earth.
Okay. But why is
Our
that?
basic, well, it's because we have evolved together with every other organism on Earth, with viruses and bacteria, and they are specially adapted to use the biological machinery of other organisms to help them survive. Whereas
Okay.
an organism on Mars, no. It's in a similar way, most extremophiles, most bacteria that say live in hot pools on Earth, do not infect human beings. They have no effect on human beings because they are specialists. They have evolved to survive in those extreme environments.
Okay. So then those
So the idea
extremophiles.
the idea of pandemics or infections coming from outer space is extremely unlikely, because they will have no adaptation to our environment or to infecting us. They'd have to get really, really lucky, or, you know, be really specialized in order to infect various organisms.
Okay. Yeah. I'm glad we cleared that up before anybody goes crazy saying that coronavirus came from space or anything like that, or
Well,
any future
it's already
pandemics.
happened. It's
Yeah.
already happened. There have been claims
Oh,
um,
right. Wow.
along those lines, yes, but they're really not credible.
Well, you heard it here. Infections did not come from space. But yeah.
It would be a bit like, you know, dropping me on Mars without a spacesuit and expecting me to survive.
Okay, that's a good comparison. So anybody who's wondering, that's quite a good analogy right there.
Yeah, yeah, it would be very, very difficult. What with an atmosphere that is below the Armstrong limit, which is the limit at which your blood boils. The pressure is so low that your blood starts boiling, which
Wow,
isn't good. You get the bend and you die, essentially.
of course. So then, if we steer back to meteorites just for a moment, how viable do you think the theory is that water and such organic compounds were brought to our planet by asteroids? So, the asteroids that I'm referring to are the C types. So, for audience members, they're the carbonaceous chondrites. They're some of the oldest things in our solar system to have been floating around.
So we think that baby planets like the young Earth have a problem with the lighter elements, so things like carbon and hydrogen, because they have a high temperature origin. Now they probably can retain some, but not enough. But material is added later to the planet. So after the planets have fully formed, there's still a lot of debris left in the solar system. And that collides with the planets. And that was a period known as the late bombardment,
Yeah.
about 4 billion years ago. So we know that these objects were hitting the Earth, and we know that they contain a lot of very interesting organic molecules. So there's a long list of them, but it includes things like amino acids like lysine.
Okay.
So they contain amino acids, sugars, lots and lots of hydrocarbons. And so it's circumstantial evidence, because we know that the origins of life occurred somewhere during that period. The first evidence for life is in some of the minerals that formed during that period. So we know the Earth's being bombarded by lots of interesting molecules at the same time as the origins of life occurred. So circumstantial evidence suggests that it probably played a role. Now, how much of a role, we don't know, because we still don't know exactly what the origins of life were.
Yeah, that's still quite a big mystery. So then, do you think that there's scope for research in that area of astrobiology?
Oh, there's huge amounts of research going on in that area. So there are lots of theories about how you get the first replicating or self-replicating organic molecule, because that's essentially what life is.
Yeah.
And all of those involve assembling complex organic molecules that do not self-replicate, so aren't living, to build up that complexity to that point that you get that one reaction that makes the self-replicating molecule. And as soon as that happens, unless it becomes extinct for one environmental reason or another, then you've done it. You've made life. And so it's all about opportunity for reactions. And as you know, chemical reactions happen really quickly.
Yes.
Most
Yes.
chemical reactions occur quickly, and given the right conditions, they are spontaneous. And so all you need is time and opportunity.
Okay.
And we've got a lot of time, hundreds of millions of years, and the entire surface of a planet to play with. So that's an awful lot of reactions. So my feeling, and it really is not much more than an opinion, is that given the right conditions, the origins of life is spontaneous,
Okay, that's
which would
interesting to know.
suggest which would suggest we should find evidence for life elsewhere in our solar system.
Okay, so then you can compare that with Earth's evidence and then make a more conclusive decision about the
Yeah.
origins of life. Okay.
So Mars is a difficult planet to find life on, because if there was life there, it's highly likely there is no life there now, but it's most likely that there was early life, and that means you need to find it fossilized. A much better bet are in the oceans of Europa and Ganymede.
Okay, yes.
There could be anything in that ocean. There could be fish people swimming around, going to work every day. Who knows? Living in shells. You know, imagine SpongeBob on Europa. Essentially that.
Wow.
And who knows? You know, we haven't yet explored that area of the solar system to that amount of detail.
Yeah, I mean, there is definitely a long time to go before we reach any of those moons like Europa. Um, but then again, you know, like on Mars, you have the Jezero crater, I believe it was, where Perseverance landed. That was a tributary, or it was part of a river, an ancient river.
Yes.
And so that is definitely some hope for the future, right?
So so the landform suggests that it's a delta.
Okay, a delta, right.
For example, like you probably know that St. Louis is built on a delta of the Mississippi River. It's one of the biggest and best deltas in the most magnificent deltas in the world. And just looking at that that structure within the crater suggests that it's a delta. And that would suggest that there was a body of standing water, because deltas form when rivers enter lakes or oceans.
Yeah.
Because the rivers are carrying sediment, they're carrying mud and sand, which is being dragged along because the water is flowing. And as soon as the water stops flowing, it has to drop its load and it builds up as a delta.
Yeah.
And we expect where there to be water, there to be much better chances of having microbial life.
Yes. Okay. Yeah, that's quite fascinating because, in my opinion, I think deltas compared to just normal rivers have more chances of holding these key components that we're looking for. Some of these organic components that we find on Earth, especially because of their capacity to drop river bed load, things like that, and also differences in velocity of the stream. All these kind of different factors, they come into play. And in my opinion, I think that is quite important in deciding where to land such rovers and where to find life. So yeah, I got it wrong. It wasn't a tributary; it's actually a delta, which you confirmed. So yeah,
So you're absolutely right, because river drainage systems anyway tend to take to concentrate components in one place. You're sampling a very large area and then you're concentrating that into the river. And of course, it's most concentrated once it reaches the mouth of the river at the delta. But all that material that's gone into solution is now in that water.
yeah, and we can just hope that it's been preserved really well in that crater. But yeah,
Yeah, whether we still don't know what we'll see. You know, there may be morphological, there may be shapes in the rocks that reveal the presence of microorganisms. So looking at the early Earth, we can see evidence for microbial mats, for microbial mounds known as stromatolites, and
yes,
just their shape is characteristic. And that would be enough to identify life. If we found a stromatolite if Perseverance found a stromatolite, I think that would be pretty conclusive of the evidence of life.
yeah. There's no way
People
we've put a
still,
stromatolite on Mars by ourselves.
no, absolutely not within the rocks, and there would still be those who would contest it, though. But I
Yeah.
think it would be fairly conclusive.
Yeah, I agree with you there totally. And for our audience members who don't know, stromatolite is basically early bacteria, cyanobacteria, which used to photosynthesize. They used to produce the specific type of solution or matrix which they used to secrete out of their cells, and it just used to build up and dry and form these loads of layers over time, and it became
Yeah.
these significant mounds on Earth. I think there's some in Australia that are quite profound. And if you just look it up, stromatolite, you'll see how wonderful these formations are.
They're still around today.
Yeah.
Stromatolites are still around today.
And they're billions of years old, which makes them really nice to look at and just to think about, which I think is awesome. I think I first came across them in a book. It's called How to Build a Habitable Planet by Charles Langmuir and uh, Stephen Brocker, I think it was. But that's quite a good book. If anybody's interested in how everything that we know became everything that we know, then read that book, How to Build a Habitable Planet. But yeah. So I just wanted to ask you something. So, asteroids, they're everywhere in space, there's millions of them. What if we mine them? Like we mine rocks on Earth, what if we mine asteroids in space? Why does that matter, Matt?
Well, part of the reason it matters is there's just too darn many of us on good old planet Earth. We've already got so many people living here that it's just not sustainable. So unless we as a civilization make the decision to reduce our numbers just by having less children, reduce the population on Earth, we need another planet. And we can go to Mars, but that's not it's not a terribly good planet. You have to live under domes. So we have to expand into space unless we want to make some really difficult decisions. And we are also now at the point that there are certain resources on Earth that are starting to become difficult to find.
Yeah.
So the classic example is nickel, where there's a global reserve of extractable nickel of about 90 million tons. Now, health warning on that figure. The amount of nickel will change depending on how much you're willing to pay for that nickel. So there's nickel in everything. Every rock you can pick up will have some nickel in it,
Okay.
but extracting that nickel would be enormously expensive. So much so that any product you made out of it nobody could afford it. So the amount of nickel that we can actually find and use is about 90 million tons.
Okay.
And currently we're using that nickel at 2 million tons per year. And probably in the next 20 years, that will be up to 4 million tons a year because it's used in rechargeable batteries.
Yes, correct.
So that means all that usable nickel is gone in about 75 years.
That's someone's lifetime.
Yeah, it's not long at all. Now, there could be lots of nickel on the ocean floors, and there are plans to extract that nickel. It's probably an ecological disaster waiting to happen because those environments on the seabed are very sensitive anyway.
Yeah.
And it involves strip mining. So unless there's a drive to make them as environmentally friendly as possible, but that still only doubles that reserve of nickel. So whatever happens, eventually you run out of metals. And the best place to get those metals is from asteroids. Whether you are returning them to the Earth, which is technically very difficult to do, or preferably actually using them in space to build structures.
Yeah. I mean, I saw somewhere, in fact, this week, in fact, yesterday, that building structures, infrastructure, rockets, space stations, all that kind of stuff, building that in space is cheaper than building it on Earth and launching it into the atmosphere, into space, and onto other
Absolutely.
planets.
It
And so,
is.
if we can, exploit those metals and the things that we use, things like palladium, osmium, rubidium, platinum, all these precious metals on asteroids, then there is actually a chance. But we haven't really got that far in mining asteroids to this date. And in fact, something that we were talking about earlier. So, for the audience members, this is going to be a bit of a shocker. There is an asteroid called Psyche 16 in space, and it is 113 kilometers in radius. That is very big. And it has enough nickel in that asteroid to meet our demands for 900 million years. Like, if you just take that in your head, 900 million years, I don't think humans are going to be around for that long. But you can just see there's so much potential in space, and we haven't even touched it yet.
The problem, of course, is always cost.
Yes.
So at the moment, yes, it would be cheaper. If you're going to build a space station, it would probably be cheaper to go to an asteroid, mine it, and use that material to build a space station, because you avoid all those lift costs. But then if you factor in having to develop the mining equipment, having to test it, not only is that hugely expensive, but there's a massive lead time there as well. That development takes a long time.
Yeah.
And if you think about investors, right? So right now, everybody's heard about Bitcoin. You know, everybody's investing in this magical money that doesn't really exist because it's possible to make money quickly.
Yeah.
You know, if it's going up, you can buy some Bitcoin, sell them 2 days later, and you make a tiny profit. But investors aren't interested if you say to them, I can double your money in 30 years' time. So the amount of time on the delivery of that investment, on the return on that investment, really matters. So currently, people really aren't willing to invest because there is no demand. There are no industries in space at the present, but there soon will be. So
Yeah.
space agencies have been looking at manufacturing in space. There are plans now to build CubeSats in orbit by 3D printing them.
Yeah. I
Now
heard about that. Yeah.
you would still need to launch the materials required to do that 3D printing. But imagine if you were a company who could turn around and say, well, you know, we will get that, we will sell you materials that we have collected in space. Then all of a sudden that's a business. And you have this ecosystem of businesses. Because currently the world's space economy, which is mainly satellites and Earth observation and telecommunications, is worth $400 billion per year.
Wow. That is
That's a
crazy.
lot of money.
That is a lot of money. I mean, I did hear about you were talking about 3D printing, and I did hear about I was listening to a podcast episode, Exponential Wisdom, with Peter Diamandis, and he founded the X Prize. And some of the teams that he's working with are actually 3D printing rockets. Can you imagine that? An entire rocket that has components that are all 3D printed. That's insane. Like, not only is that sustainable, but that will last a very long time. Um,
Yeah,
and it's very profitable as well. If you,
print it potentially easy to 3D print rockets, but printing safe rockets that can actually do what you need them to do is a lot more challenging. You know, it's difficult enough to build those on Earth without them
yeah,
exploding on the launch pad, you know.
and then imagine how many explosions we've had. Um, SpaceX very own, they had 3 rockets that exploded in the first 3 tries, and they only budgeted for 3 explosions. So, I mean, anything can happen. But I think SpaceX are doing a great job. They're definitely leading that space economy that you're talking about, not only from, commercializing space, but making it a business and ensuring that everybody has access to it by challenging people like Richard Branson, who just went into space like the other day, and also by putting things like Starlink, which is global internet from the Sahara to Everest, things like that. So I think we've entered quite an interesting age of space technology, and there's a lot to look forward to here.
It's good to see the number of players increasing,
Yeah.
because as soon as the number of interested parties increase, then prices automatically come down. Everything becomes more competitive and more open.
Yeah, it's exactly like, like Apple versus Microsoft versus IBM. It's the same thing, but off our planet, out of this world, quite literally. It's Apple versus Samsung, the same thing. Everybody's competing. Everyone wants to get to the consumers first, things like that. So I'm really looking forward to that kind of, environment, that just the vibe everywhere of combining space, business, and all those kind of aspects. It's going to be amazing.
Well, you look like somebody who would blast into space um, immediately if you could.
Definitely. I want to explore all these different frontiers. I mean, it's definitely a dream of mine, first of all, to go to the Mariana Trench, because nobody knows anything about that. And second dream is definitely to go to space. I mean, even if I don't put my foot on Mars, it will be a triumph. It'll be amazing.
Yeah, I think the age where everyday people can go into outer space is rapidly appearing.
Yes,
Uh,
precisely.
you know, I've still got my fingers crossed that I can go one day.
Yeah, I think it's likely that people like you will be able to go, especially of your stature. You've got an impressive, academic track record, and they'd want people like you on space to do the research, to get the information right. Yeah.
Well, hopefully, I'm too old.
Oh well. Well, I mean, Richard Branson's like 70 or something, and he went to space 2 days ago. So anything's possible, really, whatever
Anything's
age you
possible,
are.
yeah, absolutely. Well, for traditional astronaut training, you've got to be super fit. You've got to be in a certain role, either a flight astronaut or a science astronaut. And for people like me and you, being a science astronaut is the target.
Yes, precisely. And I think that's what Virgin Galactic were trying to do anyway by getting bioastronautics, up there. They had another researcher who's doing astrobiological missions on there as well. And they do that on the ISS, and they have been doing that for a while now, which is good to see. So hopefully that'll take off in the future. But
Well,
yeah,
astronauts are also very, very uh, they're capable of turning their hands to everything. They're great generalists, and they do not panic in any situation. I was in the Antarctic with an astronaut. We had an astronaut on our team,
okay.
and he was making beer in his tent in the Antarctic.
Wow. Very resourceful indeed.
Very resourceful, absolutely.
That takes ages, the training for you to get that mentality. But yeah. So going back to asteroid mining, do you think micrometeorites, what you're working on, can help businesses make better decisions about what asteroids to mine or where to look?
They can certainly inform us better about what's out there, the abundances of different types of asteroid. Um, but when it comes to actually making the decision to mine a specific asteroid, there is no substitute to visiting it first. And when you are spending such a lot of money just to get there and to set up a mining operation, it's worth doing that. It's worth being certain about how much resource is there and what form is it on the surface. So I think there will have to be reconnaissance missions.
Yeah, yeah, of course. And I think for the audience members, a lot of asteroids, well, most of them, I think, have iron nickel cores. And those are surrounded by layers and layers of silicon, I believe, or silicate materials. And that forms over millions of years by cooling. I may or may be wrong, Dr. Genge,
So
but
they used to be, yes, many of them used to be. So earlier in the history, they melted and they behaved a bit like little planets. So they had metal cores and silicate mantles. But the poor old asteroid belt has been battered to bits over time. And even those that melted have now largely been split up. So it's only really 4 Vista and 1 Ceres that are probably whole asteroids. And most of the others are rubble piles. So their insides are now their outsides, and their outsides are now their insides. And so most asteroids are broken up bits of pre-existing asteroids.
So I've got one last thing to ask you today. O'Neill colonies. Now, I recently found out about O'Neill colonies because Jeff Bezos was talking about them. And what these are, so basically, a physicist from Princeton in 1976, Gerard O'Neill, he proposed this idea to NASA that humans can live off Earth, but untethered from any other planet. So not living on the moon, not living on on Mars, but just floating in space in a giant donut kind of shape. So, and there would be trillions of people on these O'Neill colonies that they're called. So what do you think, Matt? Do you think they're possible?
Well, the physics is pretty simple. You just have an object that's rotating, and you live on the inner surface, say, of a cylinder, because that generates the gravity. And then you fill up your cylinder with air. You have a supply of water. You live in a landscape. You grow food in there because you reflect sunlight into the cylinder. And yeah, so that is all physically possible. The problem at the moment is we've yet to make a working, fully sustainable biosphere. So there were experiments, during the 1970s with Biosphere 1 and Biosphere 2.
I remember that, yeah.
And they completely failed.
Yeah.
These were complex ecosystems that just were too difficult to balance. And eventually they spiraled, and quite quickly spiraled, out of control. And I think that's always going to be the problem with these artificial environments in space. Keeping the ecosystem balanced so it doesn't have a catastrophic failure. Because by their very nature, ecosystems are very complicated. And it's that complexity that provides them with the resilience. It's what we're doing today to planet Earth. We are challenging the Earth ecosystems on Earth. And the only reason that they are so resilient is because of their complexity. And we're seeing that complexity decrease. We're losing species really fast. And that's a huge danger to our planet, that it's becoming less and less resilient.
Yeah, I totally agree with you there. I mean, I can see how hard it would be to replicate the conditions we have on Earth and put it in space. But I mean, it's promising. In my opinion, it is quite promising, considering we want to live for millions more years, even though that might not be possible.
Well, probably the main, the foreseeable use for them is in traveling to the stars. Because as we know, if you're traveling at sublight speeds, it takes a long time to get to other stars. It's 4 years at the speed of light to get to Alpha Centauri.
Yeah.
The nearest star cluster. And, that's 4 years at the speed of light. If you cut that down to a very small fraction of the speed of light, which would probably have to be necessary just for energy constraints, then you could be looking at 100 years to get there.
Wow.
So that's when artificial environments in which people can live their lives become really useful, and you get off your children or grandchildren get off the ship at the other end.
Yeah, exactly. I mean, I'm going to pray that it works out. Even if it doesn't, I'm just going to still pray that it does, because it just sounds like something right out of science fiction, like in Interstellar, like right at the end of the movie when he wakes up from the coma. But yeah, we'll see how that goes in the future. So, Matt, it's been great. This has been a fantastic conversation. I've enjoyed it. I hope you did too. And I hope the audience members have enjoyed it as well. So yeah, everybody in the audience, Stay tuned for the next one. And you're listening to the Earthside Show here. Thank you, Dr. Genge, for your time and for talking to me today.